Okay, so we left off, we've been talking about the different forms of quadratic functions or equations. Started off with vertex form, which really made sense for us because vertex form is the one that is closely aligned with the transformations we talked about at the start of the unit. With vertex form, you can see right away where the coordinates of the vertex are, which really just comes from horizontal and vertical translations, right? So H and K we initially talked about as being translations. Now we think about those instead. It's more convenient to think about those as the X and Y coordinates of the vertex. And A, of course, that vertical dilation factor, that part stays the same. That's still a useful way for us to get the shape of the curve from its vertex. Most recently, though, we've shifted over to standard form, okay, which, and it's not as convenient for graphing, but it has some other big advantages. Here, give me just a quick second here. Okay, so standard form, f of x equals ax squared plus bx plus c, where now a, b, and c are our parameters. We kind of started talking about that the other day. We did some practice graphing functions that were in standard form, and I bet you're probably based on when I look at the homework, it looks like people are doing pretty well on that part. But when you got to the story problems, that probably posed a little bit of a challenge because we haven't really talked about that yet. So let's go back to where we were last time. I want to show you a couple things. This is a really fun topic right here. So we started talking about using the regression feature to do quadratic regression instead of linear regression. And this was a good example we started on the other day. Okay, I've just transcribed all the information in that data table onto, as kind of we did this last time, onto this table, and I let x be x sub 1 be the number of years since 1990, and there's all our data. And if we look at the profile of that data, that's pretty clearly not linear, right? It looks quadratic. So we want to do, instead of a best fit line, we want to do a best fit parabola, right? And we can do that using any form we want to, right? We could use, we could set this up, our column of independent or input variables we called x1, the output values we called y1. And so then remember the way we do this, we put the output value column, so y1 is approximated by, so tilde, a x1 squared plus b x1 plus c. And so now it's going to fit the data to that form. It's going to pick the values of the parameters a, b, and c that best fit the data, and it did that, right? It gave us those values, and it told us that the strength of the correlation, r squared, was about 99.86% fit. That's pretty good. We could also do it down here with a vertex form if we wanted to, right? Because I've already used the lowercase a, I used the uppercase a, but I just set this up as y sub 1 tilde a times the quantity x1 minus h squared plus k. And Desmos will pick the values of those parameters, uppercase a, h, and k, to best fit our data. And unsurprisingly, we got the same strength of correlation here, right? Because it's the same data set, right? And these are just two different ways of saying the same thing, a quadratic equation. So now the next step is, and if I want to graph one of these, there's the first regression we did, there's the second regression we did. Well, look, they line up. Of course they would. They're the same parabola. Okay, the next question then is, how could we use this to predict the percentage of workers who are predicted to stay at their job in the year 2008? So that's 18 years after 1990, right? So what would I do? Anybody want to chip in here and tell me what to do? Anybody help me out? How do we do that with linear regression? If I want to make a prediction from this model that we've built, what do I do? Sarah, what do I do? Help me out.
You would just go to 18 on the x-axis.
Okay. Good. I go to 18 on the x-axis, and I got to see what the corresponding y value is, right? Okay, so there's a couple ways I could do that. I could actually just graph the I could vertical line x equals 18 if I wanted to, right? X equals 18, and I could just look for the intersection there. That's one way I could do it, right? Does that make sense? Okay, and then I could slide that value around if I want to and find other values of the intersection, but there's a better way, right? Remember that from last time we talked about regression, the regression analysis up here already set the values of the parameters that I defined. So the A, B, and C and the uppercase A, H, and K values have been assigned to those parameters by the regression. So then I could use those parameters to actually build a function. So I could come down here now and say something like f of x is equal to ax squared plus bx plus c. And look, now I've got a function, and let's change the color of that. So now look, I've got this purple graph that's not just a graph of the regression. It is a graph of the regression, but now it's a working function that I could use. Like I could come down here and say f of 18, and look, there's the output. And it gives me the output not just to a few decimal places like the intersection does. It gives me the output to a lot of decimal places. Okay, everybody got that? So that's our answer. If we're trying to round that, I probably cut off the part of the instructions that tells us what we're rounding it to, but evidently 1 decimal place, well, there it is, to 1 decimal place. That's, oh, how did we get a different answer? Huh. I must have put in a data point wrong. Did I? That's odd. That's really odd. Let's see here. 35.8, 34.1, 33, 32.9, 33.5, 35. That's really strange. So I'm guessing here that this problem from Math Excel is wrong, which is concerning to me because it's on the assignment. Has anybody done this problem? Did it work when you did this problem?
I did the assignment and I didn't have any problems.
It worked for you, huh? And you must have done it as, about the same way, right? I'm guessing here.
Yeah, I think so.
Wow, that's really strange. I don't know what's going wrong here.
Sometimes the same question varies the numbers it uses. So maybe it's just this version of the question that's wrong.
Okay. Yeah. Oh, you know what? It's possible that I did here. Yeah, it's possible that I took this answer separately from the. Yeah, I bet that's what happened. Okay. Yeah. It's going to work. I think I just grabbed this from a different question. Maybe this data table doesn't match up with this text, because I got to believe that the question is correct on this. So, yeah. So ignore the fact that that's different. I think that's my mistake in just creating this flip chart here. But that should give us the correct answer. I mean, regression always gives you the same answer. That's the beautiful thing about it. It doesn't vary at all. It's based on a statistical algorithm that always yields the same results. Okay, so then let's look at maybe one more quick example of this. The table lists the cumulative number of AIDS cases diagnosed in a country through 2005, starting in 1990. As an example, in 1993, yeah, see, look, my numbers don't match up. So that's why I've just got a different table than I do a question here. But once again, all we'd have to do with this, I've pre-built this so I wouldn't waste your time. But if we look at this data, it's not horrible, but it's not perfect either. And we would see that instantly. And let me show you this. Like if I did a linear fit here, if I did y1 is approximated by mx1, and I'll make these capital because I'm already using a b, mx1 plus b. Well, it gives me values, but look at the r squared on this. It's 98. It's not bad. I mean, it's a fairly good fit. It's a 98.12% fit, but that's not as good as we have with the quadratic one, right? The quadratic is 99.9% fit. So it's much better. And if we look at the quadratic fit comparatively, yeah, it fits that data much more closely, doesn't it? Does everybody see that? Notice that, the red parabola, boy, it goes through those points very closely. I mean, it's not very far from the points, whereas the blue linear fit, there's some places where the points are quite a bit off the line, right? Okay. We could have a big discussion about this. And honestly, if we were meeting every day, I probably would spend a little more time on this topic because it's really interesting. The whole idea of how do you pick the best fit? I'll just give you a little word of advice on this. And if we have time at the end of the year, we'll come back to this. This is one of those topics where, if it fits in, we'll discuss it. But the rule of thumb is if I pick ever and ever bigger polynomial fits, like if I did a cubic fit, it would even be stronger than this. And if I did a quartic fit, it would even be stronger than that. But the rule of thumb is that we want the weakest function that fits the data well enough, because when I start to use more aggressive functions, they're going to fluctuate much, much more wildly. They're extrapolating then for guessing data points outside of our data set. Does that make sense? Like if I picked a quartic fit, it would match this data really well, but then it would be jumping all around the place once you left the data, and we don't want that. Okay. That's just kind of a conceptual, interesting topic. It's not anything you need to know right now, but it's for those who are interested in this, and hopefully you all are. There is really a strategy in picking the best fit here on this one. Okay. All right. If I wanted to make an approximation, then what are we trying to do in the year? What does it ask us to do? I guess it doesn't. I didn't even put the question on there. But if I wanted to make a good guess, even if I want to make an internal guess, like for the year 2000, that would be the year 10, right? I'm counting the number of years since 1990. I could use the parameters for my quadratic fit to create a function. And then, so here's my function, my purple function. Oops. And then I could evaluate that function at 10. And look what I get. I get 759,814.4. Well, if I go to 19, or if I go to 2000, that's not what our data was. Our data point was 750,111. Even though that's the data that we actually gathered, our best prediction based on the model was that in the year 2000, we should have gotten this much, this many. Okay. So I can make very accurate predictions of what values should be, whether I'm interpolating, I'm picking values within my data set, the range of my data set values, or I'm extrapolating, whether I'm making guesses about the future, for example. Okay? Everybody give me a 1 to 5 on that. Okay, good. All right. So moving on. You'll have some fun with that on the assignment. I gave you some of those questions. So let's look at some applications then. So a person plans to use 220 feet of fencing to enclose a rectangular garden. What dimensions of the rectangle would give the maximum area, and what is that area? Okay, well, let's forget about the maximum part for a second. Let's just see if we can model this with a function, right? Well, they're asking about the dimensions. What do they mean by the dimensions of a rectangular garden? I mean, dimensions are what? What do we mean by that?
Length and width.
Yeah, length and width, right? For a rectangle. So if we let the width equal W and the length equal L, that's what we're trying to find. So we want to come up then somehow with, with a plan, right? Can we come up with a plan here? Can we come up with I've got two variables, so I'm going to need some kind of a system here of equations that would help us out. Or if we could come up with, I'm probably talking too much. Somebody tell me, some people have already done some problems like this. So what'd you do? What'd you do on this? Any ideas here? Maria, did you do one of these? Oh, you haven't done one of these yet? Okay. Oh, no wonder. Okay, I'm not looking at that. Is this 3.4 assignment? Is that what this? I think it is 3.4. Yeah. Okay. I guess I was looking at the wrong data on this one. You know what I'm going to do? I'm going to scoot up to real quick to something like this one first. Just occurs to me that this might be a better one to start with, and then we'll go back and we'll look at the area one next. So this is giving us the cost in millions of dollars for a company to manufacture X thousand automobiles, right? And it gives us this cost function. C of X equals this quadratic function, right? Okay, remember, X is the input. That's the thousands of automobiles being manufactured, and C is the output. We want to find the number of automobiles that must be produced to minimize the cost. Okay? Now, what would happen here if I were to graph this function? Let's look at this function in Desmos for a second. Yeah, I'm picking a new one here. Okay, so if I graph this cost function, anybody want to make a prediction, just roughly what it's going to look like, this cost function? C is our output, so that would be like the y-axis would actually be our c-axis this time, right? And x is the input, like normal. So this is the output values on this axis. These are the input values. What's the shape of this curve going to be, Rebecca Edmonds? You don't need to be specific at all, but just the basic shape of this thing. Looks like it's a quadratic function, doesn't it? Okay, is it going to open up or down? It's going to be a parabola that opens up, and we can see that. Okay, now I might have to zoom out a bit. I mean, these are these are some big coefficients there. So it's entirely possible that this is going to be, I'm going to have to zoom out a little bit to even see this thing. Okay, there it is, right? There's my parabola. If I wanted to, I could make this thing look a little better, right? I could pick a window that might display this better. Like right now, my x-axis, this is pretty tall and skinny, isn't it? It's not very convenient to look at. So this is a good skill to develop because you're going to do a lot of numerical analysis as you move forward in math. You're going to want to use things like Desmos, like graphing utilities to represent functions. They're a quick and easy way to do analysis, right? So it looks to me like, would everybody agree that this is overkill on the x-axis? I could probably just go from, let's say, negative 10 to positive, or negative 5 to positive 15 might display this a little bit better, right? So I can go up to the graph settings, go up to the wrench, and I could manually set the x parameter. So the left edge of the domain that's being displayed, look at that. Look at this. X is greater than or equal to what minimum value? Let's do negative 5. It's less than or equal to what maximum value? Let's do, or how about, and look what we get then. And so there's our cost function. They want us to find the number of automobiles that's going to minimize the cost. Well, where's that going to be on my graph? Rebecca Bertram, where's that going to be? Say that one more time. I'm sorry, I missed that.
Did you say to minimize the cost?
To minimize the cost, yeah. Where is there going to be a minimum for cost?
Would it be the vertex?
It's going to be the vertex, isn't it? Right? Because this parabola is modeling cost, and it's a parabola that opens up. And so in this case, the vertex is the lowest point, and so it's the minimum. Now on Desmos, it'll if I click on the curve, it'll realize I probably want to know that point. And so there are the coordinates of the minimum, right? How do we interpret that? See, Pagan, I know you're having issues with your mic. Olivia, interpret that for me. Interpret that result. Those are the coordinates of the vertex. And so what is the number of automobiles that's going to minimize cost?
Wouldn't it just be the lowest?
Yeah, so give me the number then. What's the number of automobiles that's going to minimize the cost?
36.
Well, that's the y coordinate, right? So that's the output. So it's 3, right? And we're measuring that in thousands of automobiles. So 3,000 automobiles, that's what that 3 stands for. That's my input, produces an output of $36 million of cost, right? Cost is in millions. That's the minimum I could get for this function. Everybody see that? Okay, this is what we do in a couple of years in calculus. We are going to spend a lot of time answering questions just like this using a process called optimization, which is it's one of the big applications of differential calculus, is finding exactly this kind of information, but doing it without a graph, okay? Well, we actually have the tools to do this without a graph right now, don't we? Because we know how to identify the vertex of a parabola, right? We can see right away, we know from the fact that this fits the form ax squared plus bx plus c, that this is a parabola, right? This is a quadratic function in standard form. So the graph must be a parabola. Because a is positive, it opens up. And so we already know before we do anything that the answer is going to correspond to the vertex, which is the minimum of this parabola. All we've got to do is find the x coordinate of the vertex. That's pretty easy to do. How did we do that? It's been a couple days, but how did we do that? Where's my pen? Oh my goodness, I lost my magic pen. There it is, my messy desk. What's our little formula for calculating the x-coordinate of the vertex. What do we call the x-coordinate of the vertex? What's the symbol for that? Natalie? We had all our parameters, A's and H's and K's and all that stuff. How do we say the x-coordinate of the vertex? Questions for Natalie? Oh, okay. Whoops. Bad mic. Maria.
Can you repeat the question, please?
Yeah. We're looking for the input value, right? We want to know the number of automobiles in thousands. So that's X. That's the input. We want the vertex, though. What symbol do we reserve for the x-coordinate of the vertex? H. It's H, isn't it? Right? And if we go back to our earlier slide here, yeah, that's H stands for the x-coordinate of the vertex, right? Okay. Now we need to find that the function that we're given is in standard form, though. So Maria, what's our formula for calculating H if I'm given a function in standard form? I'm given A, B, and C instead of A, H, and K.
Negative b over 2a.
There you go, negative B over 2A, right? Right? If we want to find H given standard form, that's the formula, negative B over 2A. So that's all we have to do in this problem, really, isn't it? And so that's going to give us negative B. Well, B is negative 24, so negative B is just the opposite of B. I get 24 over 2 times 4. Okay. Which gives me 24 over 8, which is 3. There we go. That's our answer. Right? We don't even, the question doesn't ask us to even find K. It doesn't ask for what that minimum cost is going to be. It just asks for the input value that's going to produce the minimum cost. And that's 3. Everybody give me a 1 to 5 on that. Okay, let's practice some more of these. Okay, oh, that's a good one. We'll come back to that one. We'll go back to this one for a second, right? So if I'm gonna, let's draw a picture. So there's my rectangular garden, right? We said that the width is W and the length, I guess we'll call that's maybe the length, I guess. I don't know. Probably should be the other way around. That seems backwards, doesn't it? That should be probably the length. Not that it matters, and that's the width. We want to find the maximum area. Well, how do we calculate the area of a rectangle? What's our, Liliana, how do we do that? Going back to geometry. Length times width, yeah, good. So area equals length times width. Okay, the problem is here that area has 2 input variables, L and W, right? And so we want to be able to write that with only 1 input variable. So we need to be able to make a substitution, don't we? In order to do that, we need some other information about this that's going to relate the L and the W, and that comes from here. Look at this. We're going to use 220 feet of fencing. So how can we use that to relate L and W? What does that mean, 220 feet of fencing? What does that sound like geometrically that's giving us here, Carrie? That's the perimeter, isn't it? Yeah, good. That's the perimeter. Okay, so if that's the perimeter, what's our formula for perimeter? Carrie?
I guess 2L plus 2W.
There you go. Okay, good. So if the perimeter equals 220, that's the same thing as saying 2L plus 2W equals 220. Well, look what we can do here then. When I say we want to find another equation that relates L and W, that just means we've got an equation that only has L's and W's in it, right? Now I'm able to do something like, okay, I could say, let's go ahead and solve for W here, right? If I subtract the 2L, I'm going to get 2W equals 220 minus 2L. I could divide both sides by 2, and I get W equals 110 minus L, okay? That's useful because now I've got W as a function of L, and look what I could do. I could just make that substitution up there, and now I get A is equal to L times W, but we're replacing W with 110 minus L. Okay, so if I distribute, I end up with the function A equals 110L minus L squared. If I wanted, that's quadratic, isn't it? Everybody see that? That's quadratic because it's, if I rearrange those terms, I get negative L squared plus 110L. That's in standard form where L is my input, right? What are the values of A, B, and C in this quadratic function right here? What's the value of A, Kendall?
Sorry, what was the question?
So we built this quadratic function here where our output is area, which is good because that's what we're trying to maximize, and L is our input. So instead of X and Y, we've got A and L, or L and A, right? What is the value of lowercase a? I'm looking for, this is in standard form, right? So what is lowercase a equal to? That's the coefficient of x squared, or in this case, L squared.
I don't know.
Okay, so we're just comparing this, right? We're comparing this to our standard form. You got this, I promise you do. We're comparing this to our standard form. Only our output, instead of being f of x, it's a, it's area. And our input, instead of being x, is L for length, right? But a is the coefficient of whatever the input squared is, b is the coefficient of the input to the first power, and c is the constant. See the comparison we're making? Normally it would be, I could, if it helps, I could write this as, how about this? Maybe this will help a little bit. I could write this as A of L instead of f of x.
Is it -1?
It's -1, exactly, you got it. Yeah, it's -1. So what's B?
110.
110, and C is
0.
0. Very good. Okay, so A is negative. What does that tell us about the shape of this graph?
It's going to be flipped.
Okay.
So it's going to be down.
Okay, it's going to open down, isn't it? Right. So if I were to graph this thing, sketch a graph of this, and I cannot impress upon you enough as a calculus teacher, I'll harp on this in calculus too. We'll talk a lot about this. How important it is to think in terms of graphs, right? Think in terms of graphs. If I were going to graph this function, what would a sketch of that graph look like? So this is my output is A, right? So that's the A axis, and that's the L axis. And we already know here, right? We know based on the parameters, Kendall told us that this is going to open down. And so we're going to have some vertex somewhere. Who knows? I mean, I'm not trying to be specific right now, but I know this thing is going to open down, and I'm asked to find the maximum area. Well, Kendall, where's that going to occur on my function? Where's the maximum going to be?
At the B and A.
Well, not B and A. What do we call that point that's, there's that one special point that's the turning point for a parabola?
The vertex.
The vertex. Yeah, it's going to be at the vertex, isn't it? I didn't exactly hit the target with my vertex, did I? So the vertex, here's the vertex, right? We know the coordinates of the vertex are always h and k. So we just want to know, well, first of all, what are those values, right? Because the input value is going to be my length, isn't it, in this case? So I need to know what that value is right there, because that's my input value for length, and here's my output value for area. So we just need to go up to our function up here and calculate the coordinates of the vertex. Okay, so what's our formula for calculating h? What, Jace? Jace, what's our formula for calculating h? Oh, too slow. Dlube, I'm on to you. We gotta make time here.
Is it negative b divided by 2a?
Yep. So we get negative b over 2a. So what's that going to give me, Dlube, if I plug that stuff in?
It would be negative 110 divided by negative 2.
Okay, negative over negative is positive, so I get 55, right? So the vertex is going to be at 55. How would I figure out what the output is? How would I decide on the output here? Okay. Dawson, you remember? How do I find K after I find H? I just plug it in, right? To find K, I just evaluate the function at H. So we'll do that. There's my function right there, isn't it? So I'm just going to do A of 55. Whoops. There's my function, right? Where whatever my input is, I'm going to take negative that squared plus 110 times that. Well, the input is 55. So I'm going to get negative 55 squared plus 110 times 55, which should give me 275. So that's going to be 2775. Is that right? Somebody check me on that. Is that right?
55 squared is 3,025.
3,000. Oh, what was I doing? I was way off. Way off. That's embarrassing. I'm going to get 3,000. And okay, so this whole thing, that's going to be the final answer on this thing, because I'm going to get negative that plus 110 times 55. Whoops. Is going to be 6,050. So that's going to all add up to 3,025 when I plug that in and calculate it. Okay. So that gives me some information, doesn't it? It's telling me what the value of my maximum area is, 3,025. It's telling me what L is. Okay, the only thing I'm missing is W. How do I go back and find W?
Well, you're back into the equation we started with.
Yeah, this one right here, right? The one that our equation that we use to relate the L and the W. And look, this is just like substitution in a linear system, isn't it? When we calculated W for purposes of substitution, put a box around it, because we're coming back to that when we want to find the value of W and we want to evaluate it for our answer for L, right? So W is going to end up being 110 minus 55. Well, that's 55. What do you know? Is that a surprise? If we were trying to find the most efficient rectangle for enclosing area, we got a square. That kind of makes sense, doesn't it? I bet you guys could have probably made an educated guess about that from the beginning if you'd scratched your heads a little bit and thought about it. Okay? So once again, let's review the how we did this. Okay, there's a lot of steps there, right? So we want to come up with a maximum area. Well, the first thing we got to do is we have to build a function, right? We have our input, or we define W and L. Area we know is L times W. So then that means in order for me to be able to do this problem, I've got to be able to somehow make a substitution here, right? I can't have two inputs. At this point, we can only have, in our math careers, we can only have one input. And so I've got to find some other piece of information that's going to relate L and W. In calculus, we'll call that a secondary equation. Well, it's from this other information we're given, the 220 feet of fencing, right? That gives us a perimeter, which involves an equation with L's and W's. And so then we could use that information to solve for W in terms of L and substitute, okay? In calculus, a lot of times we'll also call that an equation of constraint, because that's the thing that's constraining our problem. If we didn't impose that limit and a person wants to enclose a rectangular garden and maximize the area, well, I know what I would do. I would just make mine infinity by infinity, and I would have the biggest possible garden, right? That's kind of a dumb question though, right? So we need to have some constraint on this, or it doesn't even make sense. Well, the constraint is the perimeter, is we only have so much fencing to use. Unfortunately, D&B doesn't have an infinite supply of fencing, so I couldn't really do that. Okay, I'd have to have some constraint. Okay, give me a 1 to 5 on that. Is that making sense? Okay, this is one of those things, and we just had a day like this in calculus too, where, you know, for you guys, I'm not sugarcoating things. I mean, you're a really talented group, and so I'm pushing you a little bit with this. And it might be that this might be one of those days where you might have to come back and maybe watch this example again. You know, I can't tell you how many times I had to do that kind of thing in college, where I had to go back and revisit the material before I really sunk in. You know, sometimes it comes too fast during class to just gather it all in. So you might need to revisit it. Okay, but let's get a couple more examples, as much as we can, at least for today. How much time we got? Ooh, we're almost out of time. You know, if we need another day on this, so be it. But I want to at least get you going. Let's see if we can at least set this one up. A rain gutter is made from sheets of aluminum that are 18 inches wide by turning up the edges to form a trough, right? Everybody get what I'm saying? You've got these flat pieces. So if I look at these pieces of aluminum on edge, you know, they kind of look like this, right? Here's the leading edge, and then it kind of looks like that, right? So here's the front and there's the back edge, and they're real sharp. You can cut your fingers on them. But then I just have to bend up the edges here to create a trough. So my trough might end up looking like, you know, something like that. You get the idea? There's my trough, right? Everybody see what I'm doing there? So the question is, determine the depth of the gutter that will maximize its cross-sectional area and allow the greatest amount of water to flow. Okay? Well, in order for us to do that, we're going to have to define some variable here. Let's let x be the height of the gutter. Okay, so everybody agree then if I make this dimension right here, if I make that x, then that's also x, right? Well, if this whole thing is 18, what's the length of the bottom going to be? Yeah, it's just 18 minus 2x, isn't it? Right? Because I've bent this thing so when I bend it up, those two x's are subtracted from the total 18 length, right? And so then the cross-sectional area, well, this is the cross-sectional area right here. It's just this rectangle, right? And the cross-sectional area is just going to be the height times the width. So that just gives us 18x minus 2x squared. If I write that in standard form, I've got a of x equals negative 2x squared plus 18x. Aha, that's looking an awful lot like a quadratic, isn't it? Right? That's a quadratic that's going to turn down. And so if I want to find the maximum area, well, isn't that just going to be the vertex because that's going to be the maximum of that downturning function? Okay, get the idea? Okay, get a jump on this, on the assignment, and I'm more than happy. I want to go through a couple other examples anyway, so I'll push this deadline off. You guys have been doing a great job. Take Monday off next week. You've been doing so well. When we meet again on Wednesday, how about if I'll take like the first half of the class and maybe go through some more of these examples and push the deadline off. And then I might start talking about, I might like push into a couple other things, introduce a couple other things, but I'll make the assignments due later so you can, to accommodate for the fact that we haven't gotten through everything. Sound good? All right. I'm here after school if you need me. If not, have a great weekend, long weekend, and I will see you next week.